let me share my screen first.
Okay, I will stop this presentation now.
Okay, okay, fine. Is it visible now?
Yes, sir.
Okay, okay, fine. Then you can continue then.
Sir, it is visible, but not in the presentation mode now.
No, I will switch to presentation mode after the introduction.
Okay, okay. Sir, shall we start now?
Yeah, sure, sure.
Okay, sir. Thank you. So, good evening, everyone. It is my absolute pleasure to welcome you all to this third day of ATAL online faculty development program on strategic approaches and emerging trends in data science. Today, we have the privilege of hosting a distinguished academician, researcher, and AIML enthusiast, Dr. Shailesh Shivan from Department of Computer Science at Cochin University of Science and Technology, where he actively mentors students and doctoral researchers in artificial intelligence, machine learning, deep learning, quantum computing, and data science. His expertise spans a wide range of domains, including computer vision, natural language processing, and knowledge graph, making significant contributions to both academia and industry. With an impressive research background, Dr. Sailesh has published numerous high-impact papers in Q1 and Sci Index journals, including prestigious platforms like Nature Scientist Report, IEEE, and Springer. He has also been involved in cutting-edge projects such as European Union Horizon 2020 funded Cultural Heritage Knowledge Graph, showcasing his ability to bridge the gap between technology and real-world applications. Beyond research, he is an active contributor to faculty development programs and workshops for training professionals in industry and academia alike. Notably, he has been a resource person for over 115 faculty development programs and workshops across various institutions, sharing his knowledge and insights in AI, deep learning, and generative models. Dr. Sailesh has achieved several prestigious recognitions, including the Young Scientist Researcher Award, multiple GATE and UGC NET ARF qualifications, and the Rashtrapati Scout Award, reflecting his dedication not only to academics but also to leadership and community engagement. We are truly fortunate to have him with us today. His philosophy motto is inspire yourself, uplift others. So, on behalf of my institution, FISAT, and all members gathered here for ADAL AICTE FDP, I am happy to welcome Dr. Sailesh Shivan. Welcome you, sir.
Thank you. Thank you, sir, for the nice introduction. And I'm so privileged to be here as a part of this ATAL FTP conducted by FUSAT. Uh, Hope there are around 159 participants. Do we need to wait for some more participants?
Normally, it reaches to 230 yesterday, uh,
Okay,
but it is there is no meaning in waiting. The serious participants might have already joined.
okay, okay. Okay, sir, then we can start. I think I'm audible properly, right?
Yes,
Well,
sir.
yeah, okay. So I'm just switching off my cam. I will make more convenient in the connectivity. Okay. So participants, I request you to be interactive. As we are in the online mode, I can't see any of your faces. And in an assumption that you are all listening to my lectures properly and following it properly. So to get a feel of liveness, I may be asking some questions in between the session, and just respond by unmuting the mic as well as through the chat box. Okay, thank you. Yeah, hope the screen is visible to you, right?
Yes.
Okay. So welcome you all to the third day of this FTP, and today we are discussing about artificial neural networks, and the first part will cover the major mathematical building blocks that need to be keep in mind while discussing about artificial neural networks, and followed by that session we will be discussing about the very fundamentals of artificial neural networks to the emerging deep neural networks. Okay, and the deep neural network part is conveyed in a very layman perspective, because in the upcoming sessions you are getting more detailed explanations on each of the architectures. Still, as an introduction, I'm just making you understand what are the major things in a very abstract way happening on the deep learning domain. Okay, so in between, if you have any doubts on following the concept, you can unmute and ask. Otherwise, you can put that in the chat box. Okay, yeah. So regarding the artificial neural networks, as we know, artificial intelligence is a scientific domain that deals with making intelligence to a system with the help of data and algorithms, right? So our main intention of implementing artificial intelligence is to make a system think like a human. And we know, as in the case of human intelligence, in artificial intelligence also we can make or induce intelligence through different strategies as well as through different modalities of data, right? And one particular kind of artificial intelligence making process is actually defined using the concept of machine learning, that relies upon a concept called learn from experience, right? Learn from experience. Okay. And how we can actually realize a machine learning algorithm? You may be familiarized with different techniques in machine learning, like classification, clustering, regression, kind of techniques, right? And for each of this category of machine learning technique, like for classification, we are having different models. For regression, we can have different models. For clustering, we can have different models. And what makes these things different? The theoretical background for each of these algorithm is actually different. If you are considering naive Bayes as a classifier, or for a regression purpose, it is based on the probabilistic theories, right? And if you're considering the support vector machines, it is purely based on the linear algebra, right? And if you are considering the decision trees, it is based on different information theory based concepts. Okay, and similarly, we can have different types of different kind of algorithms based on different theories for realizing the machine learning steps. Okay, and we are today going to discuss about one prominent family of algorithms which is included in machine learning, which is called as artificial neural networks. Okay, artificial neural networks. Particularly, artificial neural networks uh, are depicting the working of the human nervous system for the purpose of thinking, optimization, and generation, right? And when you look into the mathematical understanding of artificial neural networks, basically it is based on the linear algebra, the vector spaces, and all. So it is very essential to understand the mathematical building blocks involved in the explanation of artificial neural network very thoroughly, because otherwise we are always understanding this neural network at an abstract level. So suppose you want to do some things, you want to modify some architecture, you want to put some contributions by your own, you should have the theoretical understanding of these things uh, in a very mathematical way. Okay, so the first part of this talk is focusing on such kind of very simple uh, mathematical concepts. If I again saying that they are all very simple mathematical concepts, and you have learned all these things from the class 1 to your engineering or the PG classes, but yet these are all very important. And I always feel a gap between the understanding of these concepts, the clear cut understanding of these concepts by the students, as well as even by the teachers who taught machine learning and artificial neural networks. Okay, so I'm just trying to fill that gap. Okay, so we are actually starting with the very basic concept, like equation of a line. Okay, equation of a line. And before explaining that, can you just give me the idea of what you mean by equation of a geometrical shape? We are having the equation of a circle, we are having the equation of parabola, we are having the equation of line, we are having the equation of a spline, whatever it is. Every geometrical shape is actually represented using an equation, right? So actually, what do you mean by equation of a geometrical shape? Can anyone? I'm not asking the correct answers. I'm just asking you the opinions or your views or your interpretations. It can be correct or wrong. Anyone? Equation of a geometric shape. There are around 200 participants. Please be interactive. Or you can put it on the chat too. No answers?
Please pardon, sir.
Yeah, I'm just asking about what you mean by the equation of a geometric shape.
It provides relation between one variable with other variable.
One variable with another variable.
Dependency of one variable with other variable.
Yeah, that's what an equation represents. And particularly, like, say if I climb uh, yeah, suppose I'm saying that there is a line like this, okay, and its equation is y is equal to 1 minus x. So how can we say that this particular equation is representing this line? What is the idea?
Each point in the particular shape satisfies that equation.
Exactly. Yeah. Yeah. Good. Thank you, ma'am. That is, if you consider any point on this line, okay, any point on this line, say generally it can be x0, y0, that x0, y0 should satisfy this equation, right? Okay. So what is actually mean by uh, the equation of a line? That equation will give a set of points which is on that particular geometrical shape, right? Similarly, in the case of a line, also we always relies upon the equation like y is equal to mx plus b, and in some other context we are using the equation ax plus by equal to 0, right? Ax plus by equal to 0, right? So, and this equation is actually called as slope intercept form, and this is a Cartesian form, right? And what is the need of representing a line in these two forms? Is there any significance for representing the line in these two different ways? Consider the case of y is equal to mx plus b itself, and we know this is a slope, okay, and we know this is intercept, okay, intercept, okay, slope and intercept. Particularly, what is the significance of this m and what is the significance of this b? What happened if I change the value of m? What happened if I change the value of b? You see, I can show you or give you the idea of that particular thing. With there's an application called Desmos. It's a very useful tool as a faculty who teach AI and all. This particular tool will help you to explain the concepts more easier way, and to make your presentations more easier. Like yeah. I'm using a particular tool called graphing calculator in Desmos. Okay, and you can see that y equal to mx plus, sorry, mx plus, I'm just putting it as k, okay, without any conflict, mx plus k, right? And for the particular value of m is equal to 1 and y k equal to 1, we have the equation y is equal to x plus 1, right? And this y is equal to x plus 1 is representing a line which passes through 0, 1 and 1, 0, right? So what is the significance of representing a line y is equal to mx plus k? What happens if I change the value of n? What will happen? If I change the value of n, that line will have a freedom of rotation, right? Or we are getting a rotational freedom by changing the value of m. And by changing the value of k, you will get a translational freedom, right? Okay. So why it is so significant or why it is very important? Because if you have 2 points, two or some points, maybe 2 comma 3 is the one point, right? And 4 comma 7 is the other point, okay? You can see these 2 points here, okay? And see, by adjusting the value of m and k, you can simply align this line in a particular fashion, right? You can align this line in a in an orientation what we need. Okay, and there is something called another representation ax plus by plus c equal to 0. Okay, and that will also represent a line, right? By keeping the value of a as 1, b as 1, and c as 1, the we are getting the equation like x plus y plus 1 is equal to 0. Okay, x plus y plus 1 equal to 0, and this line also, this equation is also representing a line. But if you want to align this line that pass through the same 2 points, okay, same 2 points, okay, See how many parameters I need to change. How many parameters to align the line in a way that it passes through these 2 points? How many parameters I need to tune in the first case? In the second case, it's three, right? And about the first case, about the first representation, we only need to keep 2 parameters tuned, right? Okay. And here we exactly know M is actually impacting the rotation and K is impacting the translation, right? But here it is not so clear what will happen if I change this parameter, right? So if you want to align this line, okay, if you want to align a line in a particular orientation which passes through some point, you can simply use this representation as a mean. Y is equal to mx plus k. That is why in the case of linear regression, and in some other model, we always stick for this representation, right? But when it comes to neural network, we always relies upon this particular representation, right? And we know ax plus by plus c equal to 0 with particular value of a, b, and c is representing a line, right? Okay, representing a line. This is a line. Okay. And what about the inequality ax plus by plus c greater than 0 and less than 0? What will happen? What will happen? If I give or make it as an inequality, see, we are getting a region that represented by ax plus by plus c greater than 0, right? And also if it is less than 0, another region, right? So the if the equation of this line is representing equation ax plus by plus c equal to 0 is representing a line, then the inequalities ax plus by plus c less than 0 is representing all the points in the region which is below that particular line represented by ax plus by plus c equal to 0, and ax plus by plus c greater than 0 is representing a region at the points in the region where the line which is above the line ax plus by plus c greater than 0, right? So that is why we are using the representation ax plus by plus c equal to 0 as a representation which is needed in the case of neural network. Okay. And we know the concept of vectors and vector spaces, right? And we heard about vectors at different contexts. We heard about vectors in physics. We heard about vectors in discrete mathematics. We heard about vectors in vector algebra. We heard about vectors in linear algebra, right? Everywhere we are actually uh, discussing about the particular mathematical object called vectors. So what is actually a vector? What is actually a vector? We always say like a vector is a quantity which is having both magnitude and direction, right? So what is actually mean by that? See,
A row
in
of
the
values or a column of values.
yeah, it's a column of values or a row of values. What is the physical significance of that particular uh, mathematical object? See, a vector, as I said, a vector is a quantity that is having a magnitude as well as a direction, right? So how we can actually represent this direction if you're considering a single line, if you're considering a single line, okay, okay, and taking a point 0, how many freedom of directions are there? If there is a
Infinite.
in this line,
ഇതിലായി.
in the line we can have two directions, right?
ഇത് എവിടെ ആകും?
The positive direction and the negative direction, right? Okay, okay, right. But if you consider that in a plane, we have infinite possibilities to represent the direction from an origin. Okay, we have infinite possibilities to represent a vector starting from the origin, right? So how will you represent that direction? This direction can be characterized with how it is moved towards x and how it is moved towards y, right? So if it is moved towards x and y, then we will consider one vector in the x direction I, and we consider another vector in the y direction j. Then we can say that this xi is this vector, okay, and yj is this vector. And according to the parallelogram law, we know that the resultant of these two vectors will be its sum, right? That is why this vector is represented as xi plus yj. And this I and j is a mere representation techniques, right? So what we are actually doing is we can represent this vector with this x and y as a, like this or like this, right? Or like even like this or even like this. Okay. So what I just want to say is all these things, all these representations are same. Okay. Even if you represent like this or like this or like this or like this or like this, whatever it is, they are all same, that represents a particular quantity starting from the origin towards the point x comma y. Okay, towards the point x comma y. And this how much it is traveled from 0 0 to that xy is actually called the magnitude, and the the position where the x and y is there is actually represented by the direction, right? So in that perspective, if you consider any point, okay, in any point on a two-dimensional plane, okay, if you consider a two-dimensional plane, okay, and if you consider any point xy, or here any point xy, you can say that that point can be represented by a vector, right? Are you getting the concept, right? And in the case of a three-dimensional space too, if you consider any point there, like any point like x, y, and z, x, y, and z, that is also represented by a vector with three components. And if you extend that concept, okay, if you extend that concept into n-dimensional space, okay, n-dimensional space, we know that a point on that n-dimensional space will be characterized using n components, right? N components, right? So that can also be considered as a vector starting from origin towards that point in an n-dimensional space. Okay, hope it is clear, right? Can you just put an S on the chat box if the concept is clear? Yeah. So if you think about a data set, okay, if you think about a data set, see how the data sets are actually getting represented. There will be n features, x1, x2, x3, etc. up to xn, right? So this is one data point. Then another data point will be y1, y2, etc., y3, etc. up to yn. Okay, and the other point is this is represented as x, this is represented as y, this is represented as z, and z1, z2, etc. up to zn. Okay? You can say that each of this x is a point on an n-dimensional space, y is a point on that n-dimensional space, and z is a point on that n-dimensional space, right? Okay, so these are the collection of data, and you can think that all these data points are actually a collection of vectors. Okay, collection of vectors. So we can always say that a data set is a vector space. A data set, a data set is actually a subset of a vector space. Okay, hope it is clear. Fine. So if you think about data, keep in mind that every data point is a vector, and a data set is actually representing a subset of vector space. Okay, and you have learned about the vector spaces in discrete mathematics too, right? So it can be considered as an algebraic structure, and there also we can actually say that the same concept is applied, but in a different manner. See, consider if you consider R square. Okay, R square is nothing but it is a collection of all real vectors having two components. So 2, 1, 3, 1, 4, 4, 1, 3, everything is actually a vector, and collection of set infinite number of vectors is represented by the space R square, right? Which is represented by the R square. So you can simply think about what is R raised to n, right? What will be R raised to n? It is nothing but collection of all vectors, right? Where a single vector is represented using n components, okay, r1, r2, etc. up to rn, and each of this value will be a real number, right? So we can consider this particular point in the r raised to n as a data point, right? This is represented by feature 1, feature 2, etc. up to feature n, and these are the values for that each of the particular feature, right? So if what I just want to convey to you is a data set is always a subset of what? A vector space. And if that data is represented using n features, always it is a subset of a data set is always a subset of the vector space R raised to n. Right? Hope it is clear, right?
Yes, sir.
Yeah. Now, moving into the very basic concept of line and normals. See, if you this thing you need to keep in mind as a rule, like if there is a line ax plus by plus c equal to 0, ax plus by plus c is equal to 0, and the vector ab, if you consider the vector ab, we can say that that vector AB is always normal to AX plus BY plus C equal to 0. The vector AB is always normal to AX plus BY plus C is equal to 0. That is, if you consider a line like this, okay, if you consider a line like this, okay, and it is represented by the equation AX plus BY plus C equal to 0, right? Then, if you consider the origin, if you consider the origin, any point on this line will be what? Xy. Any point on this line can be xy. Then we are saying that this vector AB will be perpendicular to, always perpendicular to this line. Okay. Vector AB is always perpendicular to this line. Right? Why it is so? Because if you consider a vector xy in this direction and AB in this direction, okay, vector xy in this direction and AB in this direction, we can say that if they are perpendicular, the dot product of this xy with AB will be equal to 0, right? That is, what is this dot product? This is AX plus BY equal to 0, right? So if you think in the reverse way, that is AX plus BY equal to 0, then the vector AB is perpendicular to this xy, right? Now we know that, see, if you have AX plus BY equal to 0, a line which passes through the center, see, if you think that way, if you think this way, that is equal to 0, then any line of the form C, if you change any value of C, that will be parallel to the initial line, right? That will be parallel to initial line. So if a vector, that will be parallel to xy line. So if a vector AB is perpendicular to, if a vector AB, okay, is perpendicular to AX plus BY equal to 0, then it will be perpendicular to all the parallel lines represented by the family of lines represented by the equation AX plus BY plus C is equal to 0, right? So that is why we are saying that the line AX plus BY plus C equal to 0, then the vector AB is always normal to AX plus BY plus C equal to 0. Okay, fine. Now we are moving into the another concept which is called as a function. We know what is a function, right? So a function relates every element in a set to each exactly one element in the other set, right? That is, if you have one set, another set, then every element in the first set is uniquely mapped into some elements in the second set, right? That is what we are calling as a function. So the first set is actually called as the domain, and the second set is actually called as the codomain. And the elements which are participating in this particular function is called as a range, right? Range. So simply a function is a mapping. Simply a function is a mapping that maps x to a particular y. Okay, that maps x to a particular y. So in that way, if you think like this set is represented by, okay, a real number set, and this is also a real number set, then all the values in that real number set can be represented using a number line, right? Okay, and all the values in the second set is also represented by the number line, right? So according to the definition of function, each element in the first domain is getting mapped to some elements in the range, right? So you having mapping like this, right? Okay. And for the convenience, what I'm doing is I'm just making this line which is perpendicular to the first line, okay, first line, and aligning it with the origin. Then what will happen? This particular point will be mapped to some points at this axis, right? And this point will be mapped to some other point at this axis, right? So the locus of all such kind of intersection can be considered as a plot of a function, right? Can be considered as a plot of a function. Okay. So likewise, we can plot f of x is equal to 50x, f of x is equal to x cube, f of x is equal to 2x. That is, every function can be plotted as a curve. Okay, every function can be plotted as a curve. Okay, and now we are moving into one of the major or important concept, but we always make mistakes on it. That is the concept of limit. Okay, the concept of limit. The limit of a function at a particular point on its domain. Okay, So if you're thinking about limits for a function at a particular point on the domain, you should be thinking about two aspects. You should be thinking in two aspects. The first aspect is there any limit exist for that function at a point? Is there any limit exists for that function at a point? And the second way is, then if it is existing, then what will be the limiting value, right? So the first thing, we need to find the existence of limit at a particular point. Then you have to find the limiting value of that particular function at that point, right? So what is actually mean by existence of limit? Okay, what is actually mean by existence of limit? It is nothing but, suppose you have a function, okay, you have a function like this, and as I said, every function can be a curve, right? Every function can be a curve. Now, if you consider a point C and you need to check whether we are having a limit at that point, okay, we are having a limit at that point. For that, what we are actually doing is, we will take two neighbors of the C, that is C minus and C minus and C plus, okay. Then what we will do is, we will just find out the value of f of C minus, okay, and f of C plus, okay. So you will get some value A0 and you will get some value B0, right? Okay, A0 and B0. Now you have to continue this experiment, okay, continue this experiment by moving the C plus to more towards C and C minus also more towards C. So just update this as C plus and update this as C minus. Okay. Again, check what is the value of C minus and C plus. Maybe it is A1 and B1. Okay. Again, move this particular C plus to more towards C and C minus also more towards C. Okay. Then also we can say that this f of C minus, okay, and f of C plus, okay, and observe the values of f of C minus and f of C plus for this particular experiment several times. So in that way, if you look into this example, see what is the function here, f of x is equal to x minus 2 whole square plus 1, right? And we need to check whether there is a limit exists for that function at x is equal to 2, okay. There is a limit exists for the function at x is equal to 2. So we have taken two neighbors, 1 unit apart, that is the first neighbor is 1 and the second neighbor is 3, right? And what are the values for f of 1 and f of 3? It is 2 and 2, right? And then we are updating that 1 as 1.5, 2 as 2.5, okay. And again we are moving more closer, that is 1.5 as to 1.9 and 2.5 to 2.1. And what you can actually observe, even from the left and right, okay, even from the left and right, if you start from 1 and moving towards 2, and if you start from 2 and moving towards 2, we can say that the values for that particular function, that is f of x minus, will somehow converge towards f of, okay, f of x plus. So if that convergence is happening, we can say that there exists a limit. Okay, we can say that there exists a limit. Okay, fine. And just think about a counter example. See, if you consider this function f of x is equal to x square, where x less than or equal to 2, and x plus 3 otherwise, okay, x plus 3 otherwise, then you need to check whether there is a limit exists for f of x is equal f of x where x is equal to 2, right? So for that, as in the previous case, we have taken one neighbor, that is 1, okay, another neighbor 3, and starting from 1 towards 1.9, 1.9.
അങ്ങനെയൊക്കെ ഉള്ള പിന്നെ ഇത്
Hello,
ചേച്ചി
sir.
ചേച്ചി എന്ന് ചെയ്യണ്ടേ ഒന്നും ആക്കണ്ട അങ്ങനെ വെച്ചാൽ അയാളാണ്
Some disturbance is actually coming from the audience side. Please mute yourself. Okay. So moving from 1 to 1.92, what happened? The value is actually converging to 1 to 4, right? 1 to 3.99, approximately it will be 4. But what about the second case? What about the second case? See, we started from the neighbor of 2 as 3, okay? And from 3 to 2.5, 2.1, 2.01, 2.001, and moving towards 2, the value is converging from 6 to 6 to an approximate value of 5. So can you observe when 1 to 2, it is converging towards 4. But when 6 to 5, it is converging to 8 towards towards from 3 to 2, it is converging towards 5.
Five.
Right? Yeah.
Yes.
So
Fine.
can you say it is f of c minus is approaching f of c plus in that case? No, right? At that point, we can say that there is no limit for this function at the point 2. There is no limit exists for the function at the point x is equal to 2. Is that clear?
Yes, sir. Yes, sir.
Yeah. Can you just put an S or no in the chat box if you are
Yes,
able to
yes,
follow
sir.
it?
Yes, sir. Clear. It's clear.
Yeah. Yeah. Now we are moving to the next. These are some other examples where the limit exists and limit does not exist. Okay. Now we are moving into the continuity, right? The continuity is a bit extension of limit. That is, in the case of limit, we said that that function is approaching to a particular value when we move x towards that particular point x0, from x minus to x0, and limit f of x plus from we move from x plus to x0. If both are equal, okay, if both are equal, we can say that that limit exists, right? But when this continuity happen, a continuity will happen when this f of x0 is equal to this convergence values. Okay, f of x0 is equal to this converging value. Then we can say that the function is continuous at x0. Okay, if the function is continuous at x0. So you may be thinking that always the functions are continuous, right? But can you just think about the situation? I will show you one function. Yeah. I'm just plotting one function y equal to 1 by, okay, mod x. Okay. See, at the point 0, what you can infer from the left and from the right, moving towards 0, you can say that it is reaching to a point, right? It is reaching to same value, right? But if you see this particular function, okay, if you see this particular function, whatever value you go towards 0, we can say that the limit exists because it is actually getting more closer and closer and converging to some point. But it will not converge at that point, right? It will not converge at x is equal to 0. So in this particular case of the function, we can say that this condition is true, right? Because moving towards 0, both the values are, that is moving towards 0, both limit x minus tends to 0, 1 by mod x minus 1, x minus, sorry, 1 by mod x minus, and limit x plus tends to 0, 1 by mod x plus, both are same. Both are getting same values, right? But we cannot say that at that point 1 by mod 0 is equal to that values, because this is infinity, right? So in some cases limit may exist, but it need not to be continuous, right? It need not to be continuous. So if the function is continuous, we can say that at that point there won't be any break, right? But see, if someone is moving, uh, someone is moving to through this line, okay, through this line, even if he travel infinitely long, he cannot jump to this line through the intersection of that point, right? That is why we are saying that that function is not continuous at that particular point. Okay, hope it is clear, right? Is it clear?
Yes, sir.
Yeah. Now the concept of derivatives. Okay, and when we are talking about derivatives, we always have a formal definition, like it is the rate of change, right? It is the rate of change, or it can be considered as the slope kind of stuff, right? So what do you mean by the rate of change? If you have a function like this, what do you mean by the rate of change? If we travel from the point x1 to x2 by taking a gap of delta x, and we got the function's values as y1 to y2, and the difference is delta y. Okay, then what is the rate of change? It is nothing but delta y by delta x, right? Or we can simply say that it is nothing but f of x plus h minus f of x by h. F of x plus h minus f of x by h, right? But this is not actually the derivative. Okay, this is not actually the derivative. Okay, if you need to make it as derivative, now it is only a difference quotient. Okay, what is that? It is only a difference quotient, and it is represented by the slope of the secant line. Okay, secant means if you have a curve and if you have 2 points, and that a line that passing through that 2 points are actually called as secant. Okay, so this particular expression f of x plus h minus f of x by h is actually representing the slope. That is, if it is theta, that tan theta is actually represented by this f of x plus h minus, sorry, sec theta. Sec theta is represented by this, right? But if you want to make it as derivative, what you have to keep in mind is you need to make this delta x to 0, okay, approximately equal to 0. Then only we can say that this secant line, okay, this secant line become a tangent at that point, right? That secant line become a tangent at that point. So if you consider this P and Q, the line PQ is a secant line, right? But if you move this Q towards P, on reaching this Q, or on the overlap of Q and P, we can say that the line is exactly passing through one point, right? At that case, we can actually say that it is derivative, right? It is derivative. Okay. Why it is actually constrained like that? See, if I show you this example, if I simply say if this is derivative, okay, df by dx, that is f of x0 minus f of x by x0 minus x as derivative instead of difference quotient. See, I can calculate that for the function f of x is equal to x square. Okay, you know what is f of x is equal to x square, right? It's having a plot like this. It's actually having a plot like this, right? And you want to calculate the derivative of that at x is equal to 1. So what all neighbors I can consider? I can consider the neighbors 0 as well as I can consider the neighbor 2, right? So I can calculate the difference quotient like this or the difference quotient like this. In this two ways we can actually find the difference quotient, right? So from left, if you calculate from 0, see, if you calculate the neighbor of x0 as 0 and x0 as 1, then if you calculate that, you will get the difference quotient as 1. And if you change that 0 to 0.1, that difference quotient becomes 1.1. If it is zero point 0.5, then difference quotient becomes 1.5. So it is not a stable value, right? Right? It's not a stable value. And if you consider the right neighbor and for calculating this difference coefficient, you will get the 3. Instead of 2, if you consider 1.9, it will become 2.9. Instead of 2, if you consider 1.5, become the difference coefficient become 2.5. But one thing you can observe is if you converge from left towards that point and right towards that point, that is, if you make this part approximately equal to 0, you are converging from 1 to 1.9 and 3 to 2.0, that you will exactly converge at the value I call 2, right? And that is the case of at 1. And if you do the same experiment for y equal to x square to find the difference coefficient at x is equal to 2, you can see that you will be converging to a value called 4. And if you consider the same function and if you're trying to calculate the difference coefficient at x equal to 3, you can see that that value is converging towards 6. So just think about the relationship. 1 at 1, the difference coefficient or the derivative become 2. At 2, the difference coefficient become 4. At 3, the difference coefficient become 6. And at 4, the difference coefficient will be 8. So what is the relationship? What is the relationship you can observe? If we have x, what will be the derivative then? 2x, right? That is why we are saying that for f of x is equal to x square, the derivative is 2x, right? The derivative is 2x. So we have covered a half part of this session. Are you clear with this? Are you able to connect the concept of derivative? Right? I just want to get more responses in the chat, please. Okay. Yeah. Thank you. So that is the concept of derivatives. So you may be thinking that for every function there exists a derivative, right? But think about this function f of x is equal to 1 minus mod x, okay? 1 minus mod x. You can say that for 1 minus mod x, the derivative is minus 1 if x greater than 0 and 1 if less than 0, right? And if you do that experiment, okay, if you do that experiment, the same experiment on the left and right side of this function, okay, left and right side of this function at x is equal to 0, you can say that the left side is always giving a difference coefficient 1 and the right side is always giving a difference coefficient minus 1. So whatever value you reduce for the h, okay, whatever value you reduce for the h, this values will not get the left and right difference coefficients, quotients will not converge to a particular value. That is, this will be always kept as 1 and this will be always kept as -1. Then we can say that for this function, f of x is equal to 1 minus mod x. At x is equal to 0, there is no derivative exists. Okay, there is no derivative exists. But see, for this function, f of x is equal to x cube. Okay, f of x is equal to x cube. If you calculate the derivative at or the difference quotient at x is equal to 0 for different values of h, you can see that they are all converging to a particular value 0. Then we can say that there exists a derivative for the function f of x is equal to x cube at x is equal to 0, right? So in this way we can understand some functions are actually having derivative and some functions are actually not having derivative at a point. Okay, then if a function is not having a derivative at a point, then that function is not differentiable. Okay, we can say that that function is not differentiable at that point. Okay, and let me drag you to the concept of functions of several variables. As I said in the previous part, see, if we have a function of the form f of x is equal to y equal to f of x, we can plot that function in a two-dimensional plane, right? Because we are relating that x to a particular y, right? So this is the point. Such kind of many points will be there, and that function is a real function is always plotted as a curve, right? So if you think or if you can extend that concept, okay, extend that concept to functions with more variables, right? So consider a function like this. Z is equal to f of xy, right? And both this x and y element of real numbers. So what are the possible values of this x and y? What are the possible values here of x and y? Any real value for x and any real value for y, right? That is, if you consider this x as a real line and this y as a real line, any point on this surface can be considered as an input towards this function, right? That is why it is represented like this. And for this particular value, okay, for this particular value, what is happening? The function f is mapping to a particular value called z, right? A particular value z, right? So this plane is actually representing its domain, and this particular axis is representing the range of that function, right? So how can we visualize this? The domain will be here, and for each value in this domain, for each point in this domain, right, you will be having a value on z. So say this value is plotted like this value is mapped to this value is mapped to this value is mapped to this is mapped to this. Then if you consider locus of all these points, then that will be represented by a surface, right? A surface on a three-dimensional space, right? A surface on a three-dimensional space, right? Now, just extend this concept into n dimension. Okay, extend this concept into n dimension. Such kind of functions are actually called as multivariate functions or functions with several variables. So, what will be the for a two-dimensional function? Okay, like y equal to f of x, that function can be represented as a curve. For a bivariate function, it will be f of y is equal to f of x comma y. That will be a plane on the, sorry, that will be a surface on the three-dimensional space. And if you consider f of x1, x2, etc. up to xn, then we can say that this will be represented by a special kind of surface which is called as hypersurface. Okay, it's called as hypersurface in the n plus 1 dimensional space. Okay, n plus 1 dimensional space. So every multivariate function can be considered as a hypersurface on the n plus 1 dimensional space, right? Now just come to the concept of partial derivatives. Okay, so we have discussed about the concept of derivative, right? So the idea of derivative is giving the, the derivative is actually giving the idea about the change happening on a function at a particular point, right? See, for this function, for this function, whatever value you consider, okay, whatever value you consider, okay, you know this function is purely y is equal to, sorry, x is equal to, sorry, y is equal to some constant k, right? And if you take the derivative, y f dy by dx is equal to 0, right? That means this particular function will not change over the values of x. That is why the derivative is derivative of this function d of dy by dx is equal to 0. But if you consider this function y equal to x, for the value of x is equal to 1, the value of y is 1. For x is equal to 2, the value is 2, right? If value of 3, the value is 3, right? So what is the derivative of dy, this function y equal to x, dy by dx is equal to 1, right? That means at every point, if there is a unit change happening on the x, that unit change is reflected on y2. Okay, that unit change is represented on y2, right? But if you consider the function y equal to x square, you are getting the derivative dy by dx as 2x, right? Dy by dx as 2x. Why it is so? Because if you consider this function from 0 to 1, okay, from 0 to 1, the change happened on y is only 1 unit, right? But from 1 to 2, the change happening on this is 3 units. And from 2 to 3, the change happening on this function is 9 unit, right? Sorry, 5 units, because the function values at 3, its values 9, right? Okay. So you can simply think like the change at each point, the change at each point itself is changing, right? The change at each point itself is changing. That is why we are having the expression 2x. Okay, that is why we are having the expression 2x. Okay, so think about a multivariate function. Z is equal to f of xy, right? Think about a multivariate function, f of xy. So I am telling that there is a change happened from z0 to z1. Okay, there's a change happened from z0 to z1. Maybe this will be the z0. Okay, this will be the z0, and this will be the z1. Right? There is a change happening. Okay, then you can actually think that this change z0 from z1 is actually contributed by some change happened on this x and some change happened on this y, right? Then how will you, that is the total change happened delta z is actually impacted by the changes delta x and delta y. I will tell you an analogy, right? Say one student is there and he studied for 3 hours. Okay, he studied for 3 hours and he had a sleep of 5 hours. Okay, he had a sleep of 5 hours. He got a mark of 50, right? And the next day he studied for 4 hours and he slept for 8 hours. Then he got a mark of 95, right? 95. So what is the difference in the mark? What is the difference in the mark? How much mark he increased? 45 marks, right? From 50 to 95. And for attaining this 45 increase, he changed his time, study time from 3 to 4, and he changed his sleeping time from 5 to 8, right? So there is an impact of 1 hour in studies and there is an impact of 3 hours in sleeping, right? So altogether we got an increase of, or altogether we have got a change of 45, right? Now my question is, if he keep the study time as 3 and the sleeping time is changed to 8, what will be the change in mark? Or even if I ask, I can ask like, if you keep the sleeping time as 5 itself and changing the study time from 3 to 4, what will be the change? Are you getting my point? Towards this total change, what is the contribution of each of the change happened on the independent variables? Okay, how can we find that? For that, we must keep one of this variable constant, right? One of this variable unchanged. Suppose we have n variables x1, x2, etc. up to xn. To find the impact of x1, we have to keep x2, etc. up to xn as unchanged, right? These things as unchanged, right? That is why here, to find the partial derivative of f with respect to x, we consider the change happened on x, that is x2 delta x minus f of comma y minus f of xy. That is, the y is kept as constant and we change the value of x to x plus delta x. And we have taken the rate of change by putting a limit to, right? And for calculating dou f by dou y, see, we have kept x as unchanged and we move from y to y plus delta y, and we are considering the change in function with respect to that particular delta y and by putting the limit y to 0, right? Now, can you understand what is the partial derivative? The partial derivative is nothing but it is giving the idea of how each independent variable is impacting, okay, how each independent variable is impacting on the change of the output variable or the dependent variable, right? So what will happen if I change a unit value on x? That will be given by dou f by dou x. What will happen if I change a unit value on y by the partial derivative dou f by dou y, right? And the physical significance is that if you consider a partial derivative with respect to x, it will be a tangent through that point x0, y0, z0 parallel to x-axis. Okay, parallel to in the direction of x-axis. And if you consider the partial derivative at x0, y0, z0 with respect to y, then it will be a line that passes through x0, y0, z0 parallel to y-axis, right? Hope it is clear, right? And I will give you an example, then that will make you more understandable on the concept. See, we have a function z is equal to f of xy. Okay, consider this function f z is equal to f of xy. Okay, and this its definition is 2x plus 3y. Okay, its definition is 2x plus 3y. Okay, its definition is 2x plus 3y. And we know the partial derivatives are dou z by dou x equal to 2 and dou z by dou y equal to 3. It is very known to us, right? Now, consider the value of this function at different combinations of x and y. See, at 0, 1, okay, at 0, 1, the function's value is 2, and at 3, 4, the function's value is 18, right? That is at the 0, 1, 0, sorry, at 1, 0, the function's value is 2. At 3, 4, the function's value is 18. So what is the difference happened on f? What is the total difference happened on f? It's 18 minus 2, which is equal to 16. Okay, 18 minus 2, which is equal to 60. Right. Now, how did we get this 16? How did we get the 16? We can calculate that. For that, you just notice what is the value changed on x? It's only 2 unit. And what is the value changed on y? It is 4 units. Okay. Okay. So now I'm just calculating this total change 16 as delta x, that is the change happened on x, into 2, and change happened on y, delta y, that is 4 into 3, right? Now just think of where did it come, this 3, 2 and 3, where did it come? This 2 and 3 are the partial derivatives dou z by dou x and dou z by dou y. So the partial derivative, that is the contribution on the change by x into how much value is changed on x, plus the contribution of y towards that change into how much value of y changed, will together give the total change happened on that function. Okay, the total change happened on that function. So are you clear? Are you clear with that? What is a partial derivative and what is the impact of it? Are you getting it?
Yes, sir.
Sir, could you please repeat that del x and del y thing, sir? Del x is equal to 2 and del y is equal to 4. Could you
Yeah,
please repeat on that?
yeah. Actually, we have considered the first point as 1, comma 0 and the second point as 3, comma 4, right? So from 1, 0 to 3, 4, what is the change happened on x?
It's 2.
2 unit.
Yes.
And what is the change happened on
0.
y?
Okay.
It is 4 unit. That is what? 2 unit and 4 unit, right?
Okay.
Now, if you know that how much change happened on x and if you know how much change happened on y, then the total change can be calculated as the change in x into the partial derivative of function with respect to x plus change in y into the partial derivative of the function with respect to y, right? So what is the significance of this partial derivative? It will give the idea of how much change will happen on the function if you change a unit x and how much value will change on z if you change a unit y. So this measure will give the idea of how much each variable impact on the change of a particular function. Is that clear?
Yes, sir. Thank you.
Now we are using this concept to find the optimization or to perform the optimization to get the optimal value, right? As I said, the derivative of a function at a particular point is actually giving the tan theta, that is the slope, right? Now you can think that if at p, if the tangent is making theta p, tangent is making theta p, the derivative of y with respect to x, dy by dx at p is equal to tan theta p, right? Okay, and dy by dx at q, dy by dx at q, this is the point q, dy by dx at q is equal to tan theta q. Okay, tan theta q. And we know that here from the example itself, the theta p is less than theta q, right? Now the theta p is less than theta q, right? That is tan theta p is less than or equal to tan theta q, right? Okay, so move starting from q, moving towards this m, moving towards this m, what will happen? The value of derivative will get decreased as the angle getting decreased, right? Then what happened at m? What will happen at m? What will happen at m? At m, what will be the angle? It become parallel to x-axis, right? So what will be the angle? Theta m will be 0, right? Theta m will be 0, and definitely tan theta m will be 0. That means derivative at that point dy by dx at 0. Dy by dx is equal to 0 at m, right? And what is the peculiarity of the point m? This point is a point you can consider as the optimal point because it is neither decreasing or increasing when it compares to the neighbors, right? And can you now think in the reverse direction? How can you find the optimum point? Derivative at a point x0 is 0 implies xc is an extremum point, which is a maximum or minimum point, then it can be used for the optimization. So how can you find the optimum point? Consider the function y is equal to f of x. Okay, consider point y equal to x of x. Find dy by dx. Okay, that is f dash of x, and equate it to 0. Then find the value of x. Then that will give the optimum point, right? That will give the optimum point. And see, these are all optimum points. If you consider the below function, these are all the optimum points for this particular function. Whenever the tangent becomes 0, the angle of inclination with the tangent becomes 0, all those points are actually the optimum point, right? Are you clear? Are you clear with that? Okay. And extend this concept into a multivariate function. See, for the function y is equal to f of x, which is represented as a curve, I can say that this point will be optimum as its derivative is 0, right? Now, what about a multivariate function? A multivariate function will have an optimum value at a particular point, have an optimum point at a particular value, only if all the tangents in x direction, y direction, or all component x's should be equal to 0. That means all the partial derivatives should be equal to 0, right? All the partial derivatives should be equal to 0. And for a function f y equal to f of x1, x2, etc. up to xn, we know that there are n independent variables, right? And we know if you consider partial derivative, there exists a partial derivative for x with respect to x1, x with respect to x2, and similarly f with respect to xn. And if you consider these derivatives as a collection, okay, these derivatives as a collection, it becomes a column, right? Column matrix, right? And as I said, a collection of values can be considered as a vector, right? So this vector is actually called as gradient of a function, right? So gradient is nothing but it is the collection of all partial derivatives of a function with respect to each independent variable. Now, what will be the condition for the optimality? For making or for finding out the optimum point, all these partial derivatives should be 0, right? This should be equal to 0, right? So that we can say that the gradient of f with respect to all the partial derivatives should be equal to 0. Now, this concept can be used to find the optimum point in a multivariate function. For that, to find the optimum point of a function, f is equal to x0, x1, x2, etc. up to xn. First, you have to calculate the gradient and equate that gradient to 0 and find the values of x0, x1, etc. up to xn. You will get the optimum point, right? Hope this is clear. And finally, I just want to give you a last concept, which is called as the error functions and surfaces, right? And you may be listening to the linear regression yesterday, right? Have you heard about linear regression yesterday? Or
Yes,
we,
sir. Yes.
yeah. So what we are actually doing is we will have a collection of x and y values, and we are approximating the relationship between this x and y as y cap is equal to what? Mx plus b, right? And we know that after approximating this relationship as y cap is equal to mx plus b, there will be a difference between actual y and y cap, right? Yeah. So how will you calculate the total error? It is nothing but sigma y minus y cap whole square, right? And it can be considered as sigma y minus mx minus b the whole square, right? And clearly you can see that this particular function j, this particular function j is depending on how many variables? How many variables? The variables m and b, right? So it's a function of m and b. Now, if you plot that as m and b for different combinations of this m and b, you will get the value of j as a function of this m and b, right? So this function is actually called as error function. J of m comma b is actually called as error function. The surface represented by that function is actually called as error surface, right? And in the case of a perceptron also, we can model this as a error surface, and we will be discussing this perceptron in the next part. Okay, so that's all for the very fundamentals which is needed for understanding neural networks. Hope the concepts are clear for you, right? And if you have any doubts, you can ask. Is there any doubts you want to ask?
No, sir.
Yeah. Can you just put the response of how you have understood the concepts on the chat box, please, everyone? Is it good or just okay or bad? Okay. So we will be having a 5 minutes break. After that, we can move to the uh, neural network part. Okay. We can have a 5 minutes break. Sir, Prasad sir, is that fine, right? 5 minutes break is
Yes,
enough,
sir.
right? Yeah. So can we start? Yes. So we are moving into the second part. Just 1 minute. Is my screen visible to you? No, 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 right?
No, sir.
Okay. Now, sir, have you shared the IPv
Yes.
the audience?
Yes, sir. I have already shared
Okay. So
in
all are
WhatsApp group. The link is
okay.
available.
Okay. So all are requested to upload that neural network.ipynb in Google Colab. Okay. So after some time, after explaining the concept, we are actually moving to do this experiment. Okay. Fine. So try to upload it. Okay. Fine. So we are going to discuss about the artificial neural network, and as just given the name dissecting neural networks, that is we are going to uh, to cut the neural networks and understand what is happening inside it. Okay, so you may be aware about the classification, right? What do you mean by classification? Technically, how will you explain classification? What's the process of classification? You will be available with the data D, which is a label data set where x comma y, where we have a data point x1, x2, etc. up to xz, element of A, x, and a small y, element of capital Y, right? Small y, element of capital Y. And our purposes or our need is to find a relationship phi that maps from x to y, right? Assume that this y is a collection of classes C1, C2, etc. up to Zk, right? And on giving a new x value, you will be getting some value Ci, right? That is the need of classification. And if we have only two classes, then we call it as a binary classification process. Okay, you have we call it as a binary classification process. So consider a binary classification problem, and we have only one feature here, and the labels are n, p, p, n, 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 like that. Only two classes are there, right? So one features and two classes. So it is a univariate binary classification problem, right? And you have to predict what is the class of 3.7. Okay, you have to predict what is the class of 3.7. So how will you predict that? For that, you first need to make a rule, right? So on visualizing the data according to the labels, that is the positive labels and the negative labels, what we have done is we have just distributed our data on a number line as it is having one feature, and from this you are able to find a pattern that you are able to find a pattern that, see, every point to the left of 4 is a negative example, and every point to the right is a positive example, right? Now we are considering this as a decision boundary. This interval can be considered as a decision boundary, and we have taken theta, the decision boundary, the threshold value theta, as 4.5, and we are making a decision rule in such a way that if p minus theta, if there is a new point p, p minus theta is less than 0, then it will return n. Otherwise, it will return p. So, according to this rule, what will be the class of 3.7? If 3.7 minus 4.5, what is that? What is 3.7 minus 4.5? Minus 0.8, right? And definitely it is a less than 0 value, right? Now, the 3.7 will be classified as negative, right? Then what will be the case if p is equal to 8.5? Can you just tell me what will be the class of 8.5? Is it positive or negative? What will be the class of 8.5? If p is equal to 8.5, what is the class? Can you just put that in the chat box? What will be the class? Is it positive or negative? Are you able to listen? Yes. Yes, so we have a decision rule like if p minus theta less than 0, we can conclude that class is negative, otherwise the class is positive. Then by considering theta as 4.5, p as 8.5, what is the class of p? 8.5. It's a positive class, right? By simply putting this on the prediction, right? Okay, fine. Now, what if the features are, or the data is attributed as x1 and x2? If you have two features and a particular outcome class, the data will be distributed over a plane instead of a line, right? So we can see that all the negative classes are clustered over here, and all the positive classes are clustered over here. Okay, and what is the peculiarity of this positive classes? If you are able to find a line like this, okay, if you are able to find a line like this, ax plus by plus c equal to 0, all the positive points are in the region represented by the inequality ax plus by plus c greater than 0, and all the negative points are represented by the region ax plus by plus c less than 0. So this can be the decision boundary. And what is the decision rule? If there is a new point p and q, then if ap plus bq plus c less than 0, ap plus bq plus c less than 0, we can say it is a negative class, otherwise it is a positive class. Hope you got it, right? Yes. Now,
Yes, yes.
extending to the concept into a three-dimensional data, that is, the data is attributed using three features. Instead of a plane, the data will be scattered over the space, right? A three-dimensional space. Then instead of a line, we need a plane to separate those classes, right? And what is the general equation of that plane? Ax plus by plus z plus d equal to 0. And see, the positive regions will satisfy the equation ax plus by plus z plus d greater than 0. Otherwise, ax plus by plus z plus d less than 0, they are all negative samples, right? Negative samples. Okay. Now, what would be the decision rule then? If there is a new point PQR, if you substitute on that equation AP plus BQ plus CR plus D less than 0, it will be negative, and otherwise it will be positive. Now, will you be able to extend this concept into a data which is attributed using n features, x1, x2, etc. up to xn features? See, as we are having two features, the equation for the decision boundary is having two variables, two constants, and a constant term, right? Two coefficients and a constant term, right? As we are having three features, okay? If it is x1, x2, xn, as we are having three features, we will be having three variables on the decision boundary multiplied with three coefficients and a constant term, right? Now, if you are having n features, what will be the general form of the decision boundary? If you are having n features, there will be n variables, each multiplied with a particular coefficient. Then there will be a constant term, right? And this equation can be now represented as sigma I equal to 1 to n wi xi plus theta, right? This is what we are calling as a hyperplane. Okay, hyperplane. Why it is called as a plane? Because it is linear in form, right? It is linear in form, and it is in the nth dimensional space. It is in the n dimensional space. That is why it is called as a hyperplane. So, what is the purpose of classification? For an n-dimensional space data, you have to find a hyperplane that properly classify the positive classes and the negative classes, and the hyperplane is actually having the form w1x1 plus w2x2 plus w3x3 etc. up to wn(xn) plus theta, and it is shortly written as sigma wixi plus theta. And on getting a new point p1, p2, etc. up to pn, p1, p2, etc. up to pn, okay, then what will be the class of this new point? You have to substitute this p1, p2, etc. up to pn in this equation. Then sigma wi pi plus theta less than 0, it will be a negative class, otherwise it will be a positive class, right? So I have not named this classifier. This is a general classifier which we uses the concept of linear algebra, right? And hope you got the idea that for the classification purpose, if you have a set of positive points in the n dimension, and if you have a set of negative points in the n dimension, you will be able to, you should be able to find a hyperplane which is in the form of sigma wi xi plus theta equal to 0. Then these regions, these negative regions will satisfy the inequality sigma wi xi plus theta less than 0, and this positive regions will satisfy the inequality sigma wi xi plus theta greater than 0. Are you clear with that? Are you clear with the concept?
Yes, sir. Yes, sir.
Yeah. Now, move to the neural network. Okay, as I said, neural networks are inspired from our biological nervous system, right? And particularly the biological neuron is having a structure like this. There will be a cell body, a nucleus, dendrite, axon, synapses, and similar to this structure, we can have a new a particular kind of neural network called perceptron. Okay, so we are moving into the concept of perceptron, which is a very basic neural network model which is invented in 1960s itself, and it uses the concept of biological neuron. for making the decisions on receiving a particular input, right? And this is the structure of a perceptron. See, this perceptron will receive x1, the inputs x1, x2, etc. up to xn, right? And it will get multiplied with a particular base w1, w2, etc. up to wn. And there is some process happening at this nucleus. What is the process? Each input will get multiplied with w1, that is w1 x1, w2 x2, and w1 xn. And all these products will get added together to form the sum w1 x1 plus w2 x2 plus etc. up to wn xn, right? And if that product, that is sigma wi xi, is greater than or equal to theta, we say the output fired is 1. Or if it is less than theta, the output fired is 0, right? So this is a condition for predicting the class using a perceptron model. And if you slightly restructure this equation as by taking this theta into the left side, okay, theta into the left side, okay. Now the decision rule will be output y equal to 1 if sigma xi by wi xi minus theta greater than or equal to 0 and sigma wi xi minus theta less than 0. Now what is this? Have you are you familiar with this particular equation? What is this equation represents? It is a hyperplane.
Hyperplane equation.
Yeah, hyperplane. So ultimately, what is the purpose of perceptron? With the help of perceptron, for a given data, we are trying to find out a hyperplane, right? Now, there may be a doubt that why I can't directly choose this theta as 0, right? Then there is no need to put this, right? If we are putting this theta as 0, then what will be the equation? Sigma wi xi equal to 0, right? Can you just consider the case of a two-dimensional data? Then it become w1 x1 plus w2 x2 equal to 0, right? This will be the hyperplane, right? Now, I just want to show you a demo. See, now, if you have a data like this, okay, the positive points are, okay, -1 1 and 1 1, okay, and the negative points are, -2 1 and sorry, -1 2 and 1 2, okay. These are the two class of points, and our hyperplane is actually having the equation like ax plus by equal to 0, right? There is no c, right? And you just try to change any value for a, right, any value for b, but you will not be able to find a hyperplane or a particular value for a and b in such a way that will separate two classes, the blue classes and the red classes, right? Why it is happening so? The equation is ax plus by equal to 0, right? So what will be the trivial solution that equation is having? Ax plus by equal to 0. What are the possible values of x and y to get satisfied by that equation? 0 0, right? Yes. And because of that 0 0, we are having a constraint that our hyperplane should always pass through the center. But if you put such kind of constraint, what will happen? You will not be able to tackle every problem. See the magic that if I introduce a C along with this, see, by changing the value of C, you can simply find the hyperplane, right? So what is the significance of this theta in this example, in this equation? That theta will give a freedom to move your hyperplane without the restriction of being in the center, right? And this theta is particularly known as bias. Okay, this theta is particularly known as bias, and generally in the model, what we are doing is we include this theta also as an input, a constant input -1 with the weight as theta, and this is what we are calling as bias. Okay, so you have understood what is the significance of bias, right? The bias will help us to move our hyperplane away from center so that we can adjust that hyperplane to tackle any problem. Clear? Now, the input to the classification problem we know is the data, right? The label data. We have a positive labeled classes and we have the negatively labeled classes, right? So what is our purpose? We have to find the hyperplane sigma wi xi plus theta equal to 0, right? So what you mean by ultimately finding the sigma wi xi plus theta? You have to find the values for wi, w1, w2, etc. up to wn as well as theta, right? And how can you find this w1, w2, etc. up to theta? That can be found using an algorithm called perceptron learning algorithm. Okay, perceptron learning algorithm. And the input to the perceptron learning algorithm is that it is nothing but a set of all inputs p with a label 1 and set of all inputs n with a label 0. So to appropriately find this w1, w2, etc. up to wn and theta, what we will do is we will initialize this particular vector w. Okay, we will initialize this particular vector w. We will initialize this particular vector w randomly. That is initialize w randomly. As it is randomly initialized, what will happen? As it is randomly initialized, what will happen? That hyperplane may not be the right hyperplane, because see, if it is a right hyperplane, it should be like this, right? The one on the one side we should have one classes, on the other side you should have other classes, right? So as it is randomly initialized, there is no guarantee that we are having it the right hyperplane. But what we are doing is we will observe the misclassification with the currently randomly initialized hyperplane. Then, using that observations that are misclassified, we will adjust this hyperplane to make it more appropriate. So, how we are adjusting? See, after initializing this W randomly, we will pick a positive observation or negative observation, right? Then we will apply that on W, and if the condition is if x is positive and w dot x is negative, that is a misclassified observation, right? Misclassified observation, because we are expecting w dot x greater than 0 as it is a positive, but we got a negative value. That is the current values of w is misclassifying x. So for that, what we are doing is we will just add x to w, and for the negative observation which gives a positive value, we will subtract x from w, right? And what is the core idea of this particular algorithm is that, see, we know this particular hyperplane is actually having the representation sigma wi xi, right? Or it can be represented as a simple dot product w dot x, right? And if this is w dot x, okay, if this is w dot x, we know that the coefficient vector w will be always perpendicular to it, right? Coefficient vector w will be always perpendicular to it. And if this is a misclassification, you know this is a misclassification, right? As it is a negative observation, it should come at this region, but this is a negative misclassification. So what we are doing is we consider this negative misclassification as x as a vector. Now its negative vector will be like this in the same direction, in the same, it is parallel to this x, and in the opposite direction we can have this negative x, right? Now using parallelogram law, Wt plus minus x, this will be the resultant, right? So if you update this Wt as Wt minus x, your new normal will be like this. So according to that normal, your hyperplane will also getting oriented in this direction, right? Now the new hyperplane will be like this. See what happened? Now the positive regions are on the one side of the hyperplane, and on the negative regions, negative points are on the other side of the hyperplane. Hope it is clear, right? Right. So whenever there is a positive misclassification, that is, you have considered a positive point and you got a negative value, you just add that data point towards the weight. And if you have a negative data point and you got a positive value, just subtract that value from the current weight. And on doing this, the W will get updated, 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 and finally you will get a proper set of values that will give a positive value for all the positive points and a negative value for all the negative observation. At that point, we can say that the model is converged. The neural network, the perceptron model is converged, right? Now, I will give you a simple example for this. See, the perceptron model is generally having the structure like the n inputs, n weights, the bias term, the bias input, the sigma, and there is something called activation function here, and it will give the output, right? I will tell you what is the significance of activation function. And just keep in mind, see, we are implementing an AND gate for using a perceptron, right? So as two input AND gate. So two input, as it is a two input AND gate, we have two inputs x1 and x2. Okay, two inputs x1 and x2, and the weights w1 and w2, the bias term -1 and theta, and we are just multiplying each weight with the input and adding this theta to get the output, right? So what is our model? Our model is nothing but, see, z is equal to w1 x1 plus w2 x2 minus theta, right? And as per the algorithm, what we will do, we will randomly initialize, okay? We will randomly initialize w1, w2, and theta. The values are 1, 1, and 2.5. So our model's equation is 1x1 plus 1x2 minus 2.5 equal to 0. And we know for the AND gate, the data will be 0, 0 is labeled as 0, 1, 0 is labeled as 0, 0, 1 is labeled as 0, and 1, 1 is labeled as 1, right? So there are three negative observations and one positive observation. These are the negative observations and this is the positive observation. If the hyperplane is right, the hyperplane should pass like this, should go like this. But now it is a wrong hyperplane. And to make it right, what we can do, we will randomly choose one input. That is the first input is 0, 1, right? And on substituting with the current hyperplane's equation, you will get 1 into 0 plus 1 into 1 minus 2.5 minus 1.5. As it is a negative observations, we got a negative value. So no error and need not to update, right? But on randomly picking the next input for the training purpose, the input is 1, 1, and it is a positive class. On substituting this on the hyperplane's equation, 1 into 1 plus 1 into 1 minus 2.5 is minus 0.5, right? But we are actually labeled it as positive, but we are getting a negative value, right? So what we will do, we will add the current input, that is the current input is 1, 1 to the current weights. Okay, we are adding up these things. So the new weights will be 2, 2 and minus 2.5. Then we are picking another data point 0, 0, which is negative, and you are getting a negative value as label. You are again picking another data point 1, 0, which is a negative observation. On applying it on the equation, you will get a negative observation, right? So at this point, we can say that if you substitute all the negative points, this equation will give, this final equation will give a negative value. And if you substitute a positive point, it will give a positive value. And after attaining this, if you visualize this particular hyperplane, you can see that, see our negative point. So the positive point is on the right side and our negative points are on the left side of the hyperplane. So starting from this particular point, starting from this particular hyperplane, what we have do, we have updated the hyperplane and made it as a right hyperplane. Hope the example is clear, right? Is it clear?
Yes, sir. It's clear.
Yeah. So on the inference part, that is inference is nothing but on giving the input to the model and observing the output. Okay, you can actually observe that. See, on giving 0, 0, the output obtained is minus 2.5. On giving 0, 1, the output obtained is minus 0.5. On giving 1, 0, it is minus 0.5. On giving 1, 1, it is 1.5, right? But our actual expected output is 0, 0, 0, 1, right? So how will you transform this current output y to the required form? You have to apply this y on a function called unit step function. See, what is the definition of the unit step function? If you are getting a value greater than 0, that will be mapped to 1, otherwise it will be mapped to 0, right? Now, minus 2.5, minus 0.5, minus 0 point will be mapped to 0, 0, 0, and 1.5 will be mapped to 1. Is it clear? Are you getting it? Right? So this unit step function is actually called as activation function. Okay, this unit step function is actually called as activation function. Okay. So now you are able to connect this particular architecture, right? The inputs are there, the weights are there, there will be a bias input -1, a bias term theta, and it all will get multiplied, and on getting the output, you are applying it on an activation function, and the results is getting as the required form. Okay, hope it is clear, right? Okay, and you can use the sklearn package for implementing the perceptron. Okay, for implementing the perceptron, and I have shared that code with you. See, this is the code. I hope you can see this, right? I hope. See, so in this example, from scalar.linear model import perceptron, we have prepared the training data 0, 0, 0, 1, 1, 0, and 1, 1, and y train. The labels are 0, 0, 0, and 1. CLF, we are creating a perceptron by specifying the tolerance value and a random state, and we are training our model by giving the x train and y train as an input. And after training, we are again applying the training data for prediction, and the ypred is the predictions. And on printing that ypred, you can see that we got the exact output as y train 0001 as output, and the corresponding coefficients, that the values of w1, w2, and theta are 2, 2, and -3, right? Are you able to connect this? You just can just try executing this one, right? You're getting a result, right? You got printed with white train, the ypred as white train itself. Then we can say the model is actually learned about the AND gate. Okay, and I can do this for OR gate too. See, I have just altered the values 0, 0, 0, 1 to 0, 1, 1, 1. That is the output of OR gate, right? And if I train the OR gate also, I got the same output as white train, as white in for white spread, and the weights are 2, 2, and -1. The weights are 2, 2, and -1. Is it clear? Is it clear? Yes.
Yes, sir.
Now, if you apply this same thing for XOR gate, for XOR, I am just changing this output as 0, 1, 1, 0. Okay, output as 0, 1, 1, 0. And on execution, you can say that you are not even getting the output as white train, right? Are you feeling it? If you change from AND to OR, it will work, and OR to XOR, it is not working. What is the problem with XOR? What is the problem with XOR? That is one of the major limitation of perceptron. That is, see, in the case of and OR, how is the data distribution? The positive classes and the negative classes can be separated using a line, right? Can be separated using a line. If you consider it in the higher dimensions on a space, it may be a plane or a hyperplane, whatever it is linearly separable or separated. It is separable by a linear equation, right? But in the OR case, will you be able to find such a line that separates two classes? Are you getting the point? Are you able to find a line that separates two classes in the OR gate? Is it possible to do so?
Yes, okay, we can use a line.
For XOR,
We can't.
we can't. That is, the problem of XOR is not linearly separable, right? The problem of XOR is not linearly separable. Okay, that is, the perceptron will fails to solve that problem. Okay, the perceptron will fails to solve that problem. There comes the introduction of the next level of network, which is called as multi-layer perceptrons. Okay, multi-layer perceptrons. So what happened is we have cascaded multiple perceptrons. So we have cascaded multiple perceptrons together and made a network of perceptrons, right? And it is in a layered manner, and particularly it is a feed-forward network. Why it is called as a feed-forward network? The outputs from one layer of neurons is feed as an input to the neurons in the next layer, and there is no backward connections. That is why it is called as a feed-forward network. And with this feed-forward network, we will be able to handle the non-linearity in our data set. And regarding this multi-layer perceptron, it is structured as three different parts. The first one is called the input layer, which receives the input. The other part is called as the output layer, and the layers in between. Okay, the layers in between input and output are actually called as hidden layers. Okay, hidden layers. Okay, fine. Now, just get into know how this XOR problem can be solved with perceptron. I don't know you have experienced the technique of XOR problem with this multi-layer perceptron. In most of the textbooks and in most of the explanations, we are actually getting confused how this is happening. So I had made my own way of explaining this particular concept, okay, and hope it will make sense to understand how it's solved. Okay, see, if you consider this XOR problem, this is the data 0, 0 as 0, 0, 1 as 1, 1, 0 as 1, and 1, 1 as 0. And we know if the data is linearly separable, we are able to find a perceptron, right? We are able to find a perceptron. If it is non-linear, we will not be able to find a perceptron, right? See, so then if you have such a data and if you simply neglect, okay, simply neglect, you simply neglect this particular input. We are actually considering only this input, and this input. Is that problem linearly separable? Can you tell me if that is that problem linearly separable? With this three data, is that problem linearly separable? What do you think? Confused? I'm just asking, is this problem by taking only these three data points? These are positive points, and sorry, this is negative points, and this is a positive point. Is this linearly separable? What do you think? Or will you be able to find a perceptron for this particular problem if you consider only three data like that? You can put that in the chat board. Is it linearly separable? Please be active. Yes, it is linearly separable, right? Now, with that data, we have found one perceptron O1, okay, with this weights. But one of the problem we face is if you give the input 0, 0, it is on this region, right? It is on the positive region. So instead of predicting it as a 0 as in the original case, it will predict it as 1. That is the only problem, right? And if you try to ignore the last input, okay, if you try to ignore the last input, and if you're considering only these 3 points, again it will be linearly separable and you will be able to find another perceptron or two, right? But the problem is the 1 1 will be predicted as 1 instead of 0, right? Now consider these two perceptrons together. We are giving the inputs 0 0 as per the table of O1, okay. O1 will give an output 1, O2 will give an output 0. And for 0, 1 and 1, 0, the O1 will give the output 1 and O2 will also be giving the output 1. And for the case 1, 1, the O1 will give an output 0, 1, 1 will give an output, O2 will give an output 1, 4, 1, 1, right? So whatever data we give to this perceptron, the possible output combinations are 1, 0, 1, 1 and 0, 1, right? And for 1, 0, on getting the output 1, 0, the actual output is 0. And on getting 1, 1, in both the cases, the actual outputs are 1 itself. And on getting 0, 1 as output, the actual output we are expecting is 0, right? So 1, 0, we expect a 0. For 1, 1, we expect a 1. And for 0, 1, we expect a 0. Now, is this problem linearly separable by considering the output from O1 and O2 as an input? And is that the actual output as Z? Yes, it is linearly separable as it is having only 3 data points, right? Now, we are able to find a perceptron for that too, right? Perceptron for that too, right? Now, you just apply each data. What will happen? If you apply 0, 0, O1 will give 1, O2 will give 0. On 1, 0, Z will give an output 0, right? And for both the cases 0, 1 and 1, 0, O1 and O2 will give the outputs 1, 1. And on 1, 1, Z will give the output 1. So we got 0 here, 1 here, and 1 here. And for 1, 1, okay, for 1, 1, the output from O1 is 0 and output from O2 is 1. On giving 0, 1 as an input, Z will give the output 0. So are we obtaining the exact output as XOR with this structure? Are you clear? Is it clear? Can you just put that in
Yes, sir. Yes, sir.
chat box? Yes. So the my intention was, with this particular structure and set of weights, with this particular structure and set of weights, you will be able to handle, the non-linearity in the data. The structure is our own decision, but how we can arrive at this set of weights is another story. It's nothing but it is what we are calling as back propagation algorithm. Okay, back propagation algorithm. Okay, so for back propagation algorithm, what we are doing is, see, before that, what is the intuition behind adding a layer? It is nothing but, see, if you are now not having any hidden layer, it is simply having a linear decision boundary. But as you add more hidden layers, the decision boundary can be more complex, so that you can tackle more complex problems. So what is the understanding you should keep in mind? If your problem is not particularly solved with a, say, specific architecture, the one thing you can do is you can simply increase the number of hidden layers, right? And for finding out the weights of hidden layers, we are using an algorithm called gradient descent method. Okay, this is an optimization technique. See, it is nothing but, see, if you have a function like this, and you know this is the optimum point, and how will you arrive at that optimum point? It is nothing but, you can start from a random point x0, right? And you just see the direction where the gradient is decreasing or the derivative is decreasing. If you move in this direction, the derivative at x0 plus will be more, and if you move in this direction, the derivative of x0 minus at x0 minus will be less. So what we will do is, we will update this particular x0 in the negative direction of derivative, that is negative direction of the gradient. And moving like this, we can ensure that at a particular iteration, we will arrive at the optimum point, right? So the equation I have mentioned is that each x0 is updated as x0 minus dy by dx at x0, right? But in the case of a multivariate function, this will be considered as the partial derivative. So x0 will be updated as x0 minus dou by dou y by dou x1 at x0, right? Clear? So this is what we are calling as what, gradient descent. And sometime if you move, if you update like this, if the derivatives are big, then you will reach here, you will reach here. Maybe you will actually skip the optimum point if you update the x0 with dou y by dou x as such, right? So what is the solution for that? Instead of, as we are having moving like this, you have to move in a more smaller step. Okay, more smaller steps. How can you do that? You just take one fraction of it, right? 1/10th of the derivative, and generally it is represented as alpha, which is called as the learning rate. So in general, what is the equation for updating a particular weight? It's nothing but theta j is updated as theta j minus alpha into dou by dou theta j of j, right? That is, each theta j is updated as theta j minus alpha into, what is that alpha? It is nothing but a learning rate with the gradient of the particular error function, right? And this concept is used in the backpropagation learning algorithm. How it is actually getting implemented? See, you can see that we are having an input. Maybe you can think like 2.5 and 5.0 as the input, and you are expecting some output y as 1. Okay, y as 1. But on giving this particular input towards this neural network, you got an output z. Okay, you got an z output 6, right? Output 6. So what is the error here? What is the value of error here? If you calculate error as y minus z whole square, what is the error? Please tell me what is the error? 1 minus 5, 1 minus 6
Whole
whole
square.
square, which is equal to 25, right? Now my question is, who is responsible for this error? Who is responsible for this error? Because of what we are getting this error?
The weights might not be adjusted
Yes,
properly.
exactly. The incorrect values of the weights are responsible for this error, right? Now we can say model this error as a function of, okay, a function of the weights W1, W2, etc. up to Wn, the weights, right? Okay, and I need to update each weight for correcting it. Now Wi is Wi is updated as Wi minus alpha into, how can I find out the contribution of W1 towards this error? What is the mathematical concept we can use here? The contribution of W1, the change in,
Taking partial derivative with respect
yeah,
to the error.
yes, exactly. That is, if you consider this dou E by dou Wi, you will get the contribution of W1 towards this error, right? With that, you can update each Wi using the gradient descent. And doing this for all the weights in the neural network in the backward pass, in a backward pass is actually called as back propagation algorithm. So ultimately nothing, you have, if you have a multi-layer perceptron structure, the structure will get randomly initialized with weights, random weights, initialized with random weights, and definitely on giving an input, it will make errors. And by calculating that error using the backpropagation algorithm, we are updating those weights with the concept of gradient descent algorithm, right? So this is exactly how what is happening in multi-layer perceptron. So what will happen at the end of training process? The weights will get adjusted, and finally you will get the output for a given input with minimum errors. Okay, minimum errors. So this is how the multi-layer perceptrons are actually getting worked. And this is one numerical example I have included in the slide. Okay, if you want, you can go through it and see. Instead of using this, instead of using this perceptron model, okay, instead of using this perceptron model, I have simply used the multi-layer perceptron classifier here. So on executing that, previously the problem was not solved, right? But here I just changed the perceptron model, okay, just change the perceptron model to a multi-layer perceptron classifier, okay, right? Multi-layer perceptron classifier, and now the problem is actually getting tackled with the multi-layer perceptron, okay, fine. And there are a lot of other methods comparing to gradient descent exist. That is what we are calling as optimizers: gradient descent, stochastic gradient descent, uh, stochastic gradient descent with momentum, mini batch gradient descent. As we are running out of time, I'm not explaining these things much, but these are all variants of different uh, optimizers, basically the stochastic gradient descent, and they are actually having difference in the formulation of equation as well as the convergence time. Some may converge more faster, some may converge more slower, right? According to the problem we are tackling, we can use any of this kind of variants. Okay, and the another part which we need to understand about the neural networks is that, see, in the binary classification problem, we have used a function called unit step function for the classification purpose, right? But sometime, instead of predicting the class precisely as 1 or 0, you maybe need to predict the probability towards the class. Okay, probability towards the class. For that, we are always using an activation function called sigmoid activation function, right? Sigmoid activation function. Okay, so instead of crisply predicting it as 0 and 1, it will make the output values or squashes the output values between the range 0 to 1. So if you're getting 0.9, that means it is having a probability in being the class 1, or if you're having a point 5, sorry, point 0.5, the model is getting confused whether it is mapping to 0 or 1. If the probability is 0.1, we can simply conclude that that observation belongs to a negative class, right? So that is what we are why we are using sigmoid. And if you want to make it in between -1 to 1, another variation of sigmoid is there, which is called as Stanich activation function. And in between the layers, okay, in between the hidden layers, some activation functions need to be used. And we always prefer this ReLU activation function for that purpose, right? This ReLU activation function. Why we are using ReLU activation function? Because there is a problem called gradient descent. Vanishing gradient problem. See, I will show you an example with this. See, uh, for updating this structure, we have to find the partial derivative of W2, theta 2, W1, and theta 1, right? And to calculate this partial derivative, we are using the chain rules. See, and for calculating W1, that is as the weights are away from the output node, for calculating the W1, we are multiplying different partial derivatives together, right? So what will happen if all these partial derivatives are less than 0? It will get multiplied and it will now converge to a value approximately equal to 0, right? Now, this particular partial derivative becomes 0. Then what will happen to the equation? What will happen to the equation? If this becomes 0, if this becomes 0, W1 remains as W1 itself, right? Because the updation will not happen for the weights. That is what we are calling as vanishing gradient problem, right? Vanishing gradient problem. That vanishing gradient problem will be tackled with the application of what? This ReLU activation function, because this ReLU activation function is not differentiable function, not a differentiable function. And there is something called loss functions. I'm just skipping this part. Okay. And finally, we are moving into the overview of deep neural networks, because it is very essential to understand what is the concept of deep neural networks when we are explaining about artificial neural networks. Okay. See, both that the both architectures you are seeing in the slide are multi-layer perceptrons, right? Both architecture you are seeing in the slide are multi-layer perceptrons. And you can think like this, red nodes are the inputs which receives the inputs like our skin or eyes or nose or ears that receive the signals. This this yellow part can be considered as our brain. The thinking process is happening at that point, and this blue dots are the output responses. Okay, output responses. Now, what is the difference in the difference between the first network and the second network? Which part is actually different? The part which represents the brain or the thinking process is actually different, right? And how it is different? The thinking or the learning happening in the second neural network is more deeper than the first one. Okay, more deeper than the first one. Okay, so what will happen in the first neural network? The thinking process is less, and in the second neural network, it is more deep. Now we can see this multi-layer perceptron is currently designed as a deep neural network, right? And there is no such tool uh, that this much layers should be there. But with the experience, the scientists are always saying that a neural network with more than 3 layers can be considered as a deep neural network. And one of the other important thing you just need to keep in mind about the deep learning architecture is that for a machine learning framework or a machine learning pipeline, you may be listening to the machine learning pipelines yesterday, right? So for the machine learning pipeline, the raw inputs need to be passed through a particular stage, which is called as feature engineering and feature extraction, where we extract the useful features from the input, and that features are actually fed into the neural network for making the decisions, right? But in the case of deep neural network, this particular stage is done by the neural network itself. Okay, the network itself, because for any problem, this feature extraction is one of the hectic stage in the machine learning pipeline, and it is covered by this deep neural network with specific techniques. And when we are thinking about different data we are handling with neural networks, the one of the data we always deals is spatial data. You can think of images as an example for spatial data, right? And the spatial data is nothing but, see, in the first case and in the second case, see, all the unit informations are available to you, but from here, will you be able to understand any information? But you are getting some information when this unit informations are arranged in a row column manner, right? So there is no meaning at this point, even though you are having all the data with you. But if that data, the unit data is arranged in a row column fashion, you are getting some meaning for it, right? That kind of data is actually called as spatial data. And when you are thinking about spatial data, we can have a dedicated architecture for that. Okay, dedicated neural network for that. And there is another data which is called as temporal data. See, if I tell you, I am actually uttering a sentence, and the words in it is, in I, India, love, terrorism, hate, and. Can you conclude that whether I am telling a positive sentence or a negative sentence from this? No, right? Because if I interpret like I love India and hate terrorism, it will be a positive thing. And I love terrorism and I hate India, it will be a negative thing, right? So even though you are having the unit informations in the unit data in the information, you need to arrange that in a time dependent way. Okay, you need to arrange that in a time dependent way, or the temporal dynamics of the data is important. Then it is called as temporal data. The audio, the text, the genomic sequences are all examples of temporal data, right? And when it comes to deep learning, the spatial data is handled with a special kind of neural network called convolutional neural network, and you will be having the session on convolutional neural network tomorrow. And you can perform a lot of tasks with convolutional neural network, the semantic segmentation, segmenting out the exact region where the object is present, the classification, the localization, the object detection, the instant segmentation. All these things can be implemented with convolutional neural network. And for temporal data, there is a specific family of algorithm called recurrent neural networks. Okay, recurrent neural network. With the recurrent neural networks, we can actually handle the temporal dynamics within the data, and there are some variations for this recurrent neural networks like uh, LSTM, GRU kind of stuff that will also be covered in the next session, I think. I'm just giving the overview of what all things are there in the deep neural network. And it can be utilized for sentiment analysis, text summarization, question answering, machine translation kind of steps. And dedicated architectures are available for graph data, which is called as graph neural networks. And with that, we can do the graph classification, node classification, link predictions, community detection, graph embedding, graph generation kind of steps. And the major kind of models currently we are talking about is the generative models, that is generative deep learning models, generative AI models. And what is the actual difference between the generative models and the other traditional models? It is nothing but, see, in the case of CNN or RNN or the perceptron or multi-layer perceptron, we always use that models for making a decision. Okay, for regression or classification, for forecasting, whatever it is, we are always using it for the prediction purpose, right? Or for making a decision. So such kind of networks are actually called as discriminative models. Okay, discriminative models. But apart from making a decision, we can actually generate something, right? Suppose here I'm giving an image of a dog and predicting whether it is a dog or not. Okay, predicting whether it is a dog or not, then it can be a discriminative model. But on giving a particular image of a dog, of a puppy, and you are generating the image of another dog, which is equivalent to the after 5 years how this puppy will looks like, then there we are actually generating something out of the input, right? Such kind of models are actually called as generative AI models. Okay, and this generative AI models can be done with text to text, image to image, text to images. And the most major architectures we always use in the generative models is encoder decoder models. These are the encoder decoder models. With that, you can do the semantic segmentation, the instant segmentation, the super resolution, denoising purpose, the colorization. And for text, you can do the machine translation, text summarization, chatbots kind of stuff. Even you can combine the images and text for encoder decoder. Like here, the input is an image, the output is a text, and the basic concept is from the input modality you have to generate some output in another modality or in the same modality, right? And generative adversarial networks are there. That is for the again generative purpose. You may be familiarized with or you may be heard about the deep fake architectures, right? Deep fake. So such deep fakes are actually generated using the generative adversarial networks, and the transformers are the secret behind the LLMs, the chat GPT, the Gemini kind of stuff, right? So the transformer architectures are actually the secret behind this GPT kind of models. And the main the concept we have used in such kind of networks are actually called as attention. Okay, attention mechanism. With the help of attention mechanism, the transformers are achieving such kind of wonderful or magical capabilities. And for images, there is a counterpart which is called as vision transformers. And finally, we are talking about the diffusion models, where DALI, right? On giving a particular prompt, you can make images out of it, right? So that kind of applications are relying upon a architecture called diffusion models, right? So these are the things, the state of art techniques you need to explore if you want to be in the deep learning domain. Okay, and there are a lot of other things are actually coming up, but most of the researchers and the application developments are based on these techniques, like the CNN, the RNN, the graph neural networks, the autoencoders, the GANs, diffusion models, transformers. These are the basic algorithms always available in this deep neural network domain. So, so we are moving into the end of the session. Hope you had a great time in this 3 hour span. So I'm dedicating the last 10 minutes for a Q&A session. If you have any queries or if you have any doubts, or even you can give some feedbacks on my session. Uh, thank you all for the patient listening and being interactive while the session. Thank you.
Participants
Yeah, good
can
evening,
ask
sir.
questions.
Yeah, good evening, sir.
Yeah,
Uh,
good evening.
uh, First of all, thanks a lot for this wonderful session. It's really informative. Sir, I had a question with respect to the global minima and local minima. Like
Okay.
during the convergence of our model, we always prefer our model to converge towards the local minima as compared to
Okay.
global minima. So can you please explain me, I mean, what is the main logic behind the same? Like,
Yeah, actually, we are always taking our data as a subset of the universal vector space, right? As I said. So for a given data set, if you calculate the error function, right, for predicting whether it is a classification or regression, whatever it is, if you model your loss function, and it is highly depending on the data, right? So we always get a surface, a error surface, which is having a convex nature, right? And this convex nature makes this error surface optimized to be on a particular subset of our data, or a particular set of given data, right? So that with that particular set of data, this error minimizations need to be done in a local manner, because we don't have the universal data set to handle every edge cases, right? We only have to deal with the similar data which is available for our training purpose. So it is always okay to be in the local minima rather than the global minima. Is it
thank you,
clear?
sir. Yes, sir. Thank you, sir.
Participants, any more questions?
Sir,
Yeah,
sir, with respect to Gen AI, like we commonly face the problem of hallucinations.
yeah.
So, is it suffice to is it enough to just have a knowledge-based system just to overcome those hallucinations, like, or we can try to combine some algorithms of our own with help of the knowledge base and try to create certain policies, like in Q-based learning we try to create certain we try to follow different policies and all.
Yeah.
Like, is there any other alternative?
Yeah, actually, there are a lot of techniques to handle the hallucination. The proper fine tuning on the data itself is somehow mitigating the hallucinations. And but as we are having the constraints of data as well as the resources, the pre-training and the fine tuning is a bit difficult or a cumbersome task, right? So the most adapted technique by dealing with hallucination is that the RAG, different kind of RAG models. Right? Have you heard about the agentic RAG or the advanced RAG system that utilizes the knowledge graphs and the internet resources to mitigate the hallucination?
Yes, I heard about that, but
Yeah,
I have not gone through it in a deeper way.
yeah. Actually, you can make use of that. That is what we are calling as agentic RAG or advanced RAG systems that utilizes the knowledge graphs, prompt engineering, as well as the internet resources, the live internet resources for dealing with this hallucination.
Okay, sir. Thank you, sir.
Yeah. So there is a question in the chat box for summarizing the text. Which transformer model is better? Uh, Actually, the one thing you have to keep in mind while dealing with any machine learning model is that there is no particular model works well for all the data for all the use cases, right? So you can have a baseline of which model can be used. Like if you like you asking which transformer, we are always using the BERT or the GPT for the summarization, and there are some variations of BERTs are there, Robert kind of stuff. So such can that can be used, but it's always a trial and error method to try with different models and come out with the best one.
Thank you, sir. Hello.
Yeah.
Good evening, sir.
Okay. Yeah. Tell me, ma'am. Good evening.
In gradient descent,
Yeah.
suppose if we take the local minima,
Yeah.
it will lead to oscillation problem.
Yeah.
Then what is the solution, sir?
You can actually adjust the learning rate for that one, or you can do some kind of regularization techniques that can smoothen the error surface. So if small local minimas are there, that will get smoothened, and you can actually move to the actual minimum optimum point.
Thank you, sir.
Yeah. And one more experiment actually I can demo. Sorry that I forgot it. So this is a simple demo on how we can apply this multi-layer perceptron on the iris dataset for the classification purpose. See, we have, is my screen visible to you?
Yes, sir.
Yes, sir.
Yeah. So we have just loaded the data from sklearn itself, the iris data, like see iris, the data and the labels are there. And before moving into modeling our problem, what I have done is like I need to check whether the perceptron or the multi-layer perceptron is better suited for the problem, right? So for that, what I have done is I have taken the iris data set, the features in X and the labels in Y, right? Then I have applied PCA for the features and make it into three features. Okay, reduce it into three features, and these three features are plotted as a 3D plot. Okay, 3D scatter plot. Okay, on the 3D scatter plot. Okay, see, and clearly from the figure itself, see the observations are actually overlapping to each other, right? So the linear model will not help us. That is, the perceptron will not help us. So what we are doing is we are just moving to multi-layer perceptron. For that, we are just splitting the data into training and testing, X train, X test, Y train, and Y test. Okay. Then we are using the multi-layer perceptron classifier with this. solver. Solver is the optimizer, ADAM, and we are using this learning rate as 0.00005, that is 10 raised to minus 5. Then the hidden layers, there are 2 hidden layers. Each of the hidden layers will be having 100 neurons, right? If you want to add more hidden layers, then you can add like this. Okay. And the random state is the seed to the random number generator, and tolerance is the error tolerance, and how much iterations the multi-layer perceptron will iterate to train the weights. That is the uh, things we have given as the hyperparameter. Then we are actually training our model and predicting on the test data, and on calculating the accuracy we are getting 100% result with this multi-layer perceptron classifier. And to observe this result, I'm just plotting it as a confusion matrix. See, we are having a proper classification for all the 3 classes, and all the matrices are now uh, 1. The precision, the recall, the difference score, everything is actually 1. So such a simple thing to implement a multi-layer perceptron with this SKLL. And if you are moving to deep neural networks, definitely the SKLN package is not enough, as the deep learning is more with more computationally intensive operations. We need to utilize the parallel computing and optimization techniques. For that, you can either go for TensorFlow or Keras or uh, Py, uh, PyTorch kind of frameworks. Okay, yeah.
Thank you, sir.
Yeah.
I think there is no more questions. I request Assistant Professor of Research, Mira Teresa, for the vote of thanks session.
Thank you, sir. Good evening, everyone. It's my privilege to extend a vote of thanks as we conclude today's session of 6-day faculty development program on strategic approaches and emerging trends in data science. First and foremost, I would like to express our sincere gratitude to our esteemed resource person, Dr. Sailesh Shivan, Assistant Professor, CUSAT. Your expertise in the field and the engaging session was truly has truly enlightened us, deepening our understanding of neural networks and its scenario of working. I also want to take this opportunity to thank all the participants who joined us in today's session. Your active participation, questions, and discussions have enriched this session, making it even more engaging and valuable to everyone involved. Once again, thank you to Dr. Sailesh and the participants. Tomorrow's session will be on convolution neural networks. The session is handled by Dr. Sumod Sundar, Associate Professor, TKM College of Engineering, and the session will be from 6 to 9. Again, thank you so much to everyone. Have a great night and see you tomorrow.
Good night. Good night to all. Bye.
Good night. Thank you.
Thank you, sir.
Thank you.